The comfortable lie we all believe about reality for most of human history. We lived inside a comforting lie. The lie is simple: reality exists independently of us. The world is out there, solid and objective, waiting patiently while we observe it. A rock is a rock whether or not anyone looks at it. A tree falls in the forest whether or not ears are present. The universe runs like a machine, cold, mechanical, indifferent. This idea feels obvious, it feels safe, it feels common sense. And Richard Feynman warned us that common sense is exactly where physics becomes dangerous. Because the deeper physicists looked into nature, the more that comforting picture began to crack. Not metaphorically, literally. At first, everything seemed fine. Newton's laws worked beautifully. Planets obeyed equations. Objects followed predictable paths. Measurement was passive. You looked, and the universe politely revealed its secrets. But then, something strange happened. When scientists started measuring things very carefully, at very small scales, reality began behaving rudely. Particles refused to sit still. Outcomes changed depending on how you looked, and asking a question altered the answer. This wasn't philosophy. This wasn't mysticism. This was experimental fact. Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Not because physicists were stupid, but because reality itself stopped making sense. And the first crack appeared when we realized something terrifying. Measurement is not neutral. The act of observing reality does not merely reveal it. It interferes with it. Imagine trying to measure the position of a tiny particle, an electron. You can't just look at it. You must interact with it. You must bounce something off it. And that interaction changes its motion. So which position was real? The one before measurement or the one created by measurement? Classical physics had no answer. Quantum physics offered a disturbing one. There is no reality independent of measurement. Not in the way we imagine. Feynman didn't say this to shock people. He said it because experiments forced him to reality. It turns out it's not a stage where events play out. It is more like a negotiation between what exists and what is asked. And once you see that, the universe never looks the same again. The experiment that shattered objectivity, if there is one experiment that should make you deeply uncomfortable, it is the double-slit experiment. Not because it is complicated, but because it is simple and devastating. Imagine a wall with two narrow slits, behind it a screen. You fire tiny particles, electrons, toward the slits, one at a time. If electrons were ordinary particles, you'd expect two bright bands on the screen, one behind each slit. But that's not what happens. Instead, an interference pattern appears, a pattern of waves, light and dark bands, as if each electron passed through both slits at once and interfered with itself. This is already strange, but it gets worse. Now place a detector at the slits, just to check which slit the electron goes through. The moment you measure it, the moment you ask the question, the interference pattern disappears. The electron behaves like a particle again. Nothing else changed. Samey electrons, samey slits, samey screen. Only one thing changed. You looked. Feynman called this experiment the heart of quantum mechanics. Not because it's impressive, but because it cannot be explained without abandoning classical reality. The electron does not have a definite path unless you force it to have one. Before measurement, asking, which slit did it go through, is not just unanswered, it is meaningless. Reality at this scale does not commit to facts until questioned. And that is not a poetic interpretation. That is what the mathematics and experiments demand. Feynman emphasized this relentlessly. Do not try to imagine what the electron is really doing. There is no hidden story behind the scenes. Nature does not behave like things we're familiar with. It behaves like nature. The moment you insist on classical explanations, you create paradoxes. The moment you accept the math, everything works, but your intuition collapses. Because this means reality is not fully formed until interaction occurs. Observation is not a camera. It is a hammer. Why measurement is an act of violence, we like to imagine measurement as gentle. A thermometer quietly reads temperature. A ruler calmly reports length. A clock politely ticks. But at the quantum level, measurement is brutal. To measure something extremely small, you must disturb it. There is no way around it. This isn't a technological limitation. It's a fundamental feature of the universe. Feynman explained this using momentum and position. To know a particle's position precisely, you must confine it. That confinement requires high-energy interactions, and high energy means unpredictable momentum. The more precisely you measure one quantity, the more violently you disrupt another. This is not because we are clumsy. It's because reality refuses to be fully known. The Heisenberg uncertainty principle is often misunderstood. It is not about ignorance, it is about structure. The universe itself is built so that certain properties cannot simultaneously exist as definite values. Measurement doesn't reveal pre-existing facts. It creates them. This is where people panic and bring consciousness into the picture. They ask whether the mind collapses reality. Feynman hated this question, not because it was stupid, but because it was unnecessary. The problem is not consciousness. The problem is interaction. Any interaction that extracts information counts as a measurement. No human required. Reality breaks not because you think about it, but because you touch it. And the universe is made of things constantly touching each other, which raises a disturbing possibility. There may be no observer, independent reality at all. The collapse that nobody can explain quantum mechanics introduces a strange concept, the wavefunction. It is not a physical wave. It is a mathematical object. It describes all possible outcomes. Before measurement, the system exists in a superposition, a spread of possibilities. After measurement, one outcome appears. This transition is called wavefunction collapse, and literally nobody knows what causes it. Feynman openly admitted this. The equations describe how the wavefunction evolves smoothly over time, but measurement introduces a sudden jump. Two different rules, two incompatible processes. Why, no one knows. Some interpretations say collapse is real. Others say it only appears real. Some say all outcomes occur in different universes. Feynman refused to commit. His position was radical in its humility. Shut up and calculate. Not because understanding doesn't matter, but because pretending to understand is worse. The math works. The predictions are perfect. Reality behaves accordingly. Or discomfort is irrelevant. When reality depends on the question, one of the most unsettling implications of quantum physics is this: different questions produce different reality. Not different answers, different physical outcomes. Measure position, and the particle has a position. Measure momentum, and it has momentum. But it cannot possess both simultaneously. This is not about incomplete knowledge. It is about incompatible realities. Feynman emphasized that physics is not about how nature is. It is about what nature does when tested. Reality is not a book waiting to be read. It is a conversation, and the question shapes the response. This destroys the idea of a single, objective description of the world. There is no God's eye view. There is only interaction. Why classical reality is an approximation if reality is so unstable? Why does the world feel solid? Why don't chairs blur into probabilities? Because quantum effects cancel out at large scales. Decoherence happens. Interactions multiply. Possibilities collapse rapidly. Classical reality emerges not as truth, but as convenience. It is a statistical illusion. Feynman loved this idea. The world we experience is not fundamental. It is an approximation that works well enough. Physics does not promise comfort. It promises accuracy. Chapter 7, Feynman's quiet warning. Feynman never claimed reality was unreal. He claimed our expectations were wrong. The universe is not obligated to make sense to us. Measurement is not passive. Observation is not innocent. Reality is not finished until touched. And the more precisely we ask questions, the more violently the universe responds. That is not mysticism. That is physics. And Feynman warned us quietly, calmly, without drama, that the deeper we look, the less the universe resembles anything we expected. The dangerous illusion of what really happened. Human beings are obsessed with one question: what really happened? We ask it in courtrooms. We ask it in history books. We ask it after arguments, accidents, and catastrophes. We believe deeply that for every event there exists a single definite story, one sequence of facts, one objective truth, waiting to be uncovered. Physics once shared that belief, and then measurement destroyed it. Richard Feynman understood something profoundly unsettling at the fundamental level of reality. What really happened is often the wrong question, not unanswered, wrong. In classical physics, events unfold like a movie reel. Each frame follows the last. If you rewind far enough, you can reconstruct the entire story. But quantum physics refuses to behave like a movie. It behaves more like a list of possibilities, until you demand a specific outcome. Consider a simple quantum event: an unstable particle decays. When did it decay? Before measurement. The particle exists in a superposition of decayed and not decayed states. The mathematics does not assign a single moment of decay. It assigns probabilities over time. Only when you measure do you get a definite answer. So what was the decay time before measurement? There wasn't one. This isn't ignorance. This isn't missing information. The universe itself did not commit to a specific history. Feynman emphasized that quantum mechanics does not describe a hidden timeline unfolding behind the scenes. It describes what can be said about outcomes when experiments are performed. And that distinction changes everything. In everyday life, we believe the past is fixed, immutable, locked in stone. Quantum mechanics quietly suggests something more disturbing. Some aspects of the past are not fully defined until the present interacts with them. This sounds outrageous, but it is experimentally supported, delayed. Choice experiments show that choices made after a particle has passed through an apparatus can influence how its past behavior is described. Did the particle act like a wave or a particle? The answer depends on what you measure, sometimes even after the fact. This does not mean we change the past like a science fiction movie. It means the past was never a single story to begin with. There was a range of possible histories. Measurement selects one. Feynman was careful here. He did not claim reality is subjective. He claimed it is conditional. The universe does not maintain a detailed ledger of events independent of interaction. It maintains rules. And when interaction occurs, the rules produce outcomes. This destroys the comforting idea that physics is about uncovering a pre-written script. Physics is about constraints on what can happen, not guarantees of what did happen. When we ask, what really happened? We are often importing a classical assumption that no longer applies. At the quantum level, reality does not owe us a narrative. It owes us consistency. And consistency is exactly what quantum mechanics delivers. At the cost of our intuition, this is why Feynman repeatedly warned students not to visualize quantum events in familiar terms. When you try, you smuggle in assumptions about definite paths, definite times, definite properties. Those assumptions break the theory. Reality doesn't break. Your expectations do. The most dangerous illusion is believing that the universe must have behaved in a way that makes sense to you, even when the equations say otherwise. Feynman's genius was not in making quantum mechanics feel intuitive. It was in refusing to lie about how strange it really is. Probability is not ignorance. It is the fabric of reality. Most people think probability exists because we don't know enough. If you flip a coin, you say there's a 50-50 chance of heads or tails, not because the outcome is mysterious, but because you didn't measure the force, the angle, the air resistance. The exact shape of the coin in principle, you believe the result was determined all along. Probability, in this view, is a confession of ignorance. Richard Feynman warned that this intuition fails completely in quantum physics. At the fundamental level, probability is not a shortcut for hidden certainty. It is the certainty. When quantum mechanics tells you there is a 30% chance of one outcome and a 70% chance of another, it is not saying we don't know which one really happens. It is saying that is all reality is willing to specify. There is no deeper answer beneath the probabilities. This idea is profoundly disturbing because it attacks a belief so basic we rarely question it, that events must have definite causes, producing definite outcomes. In classical physics, probability is temporary. In quantum physics, probability is permanent. Feynman emphasized this again and again. The equations do not describe particles moving along unknown paths. They describe amplitudes, which are complex numbers whose squared magnitudes give probabilities. And those probabilities are not placeholders. They are the final product. When an electron hits a screen, quantum mechanics does not tell you where it will land. It tells you the probability distribution of where it might land. And nothing, absolutely nothing, inside the theory selects the specific spot. The universe simply chooses. This makes people uncomfortable, so they try to smuggle certainty back in. They imagine hidden variables. Secret instructions carried by particles determining outcomes behind the scenes. Feynman paid close attention when physicists tried this. And then came Bell's theorem. Bell proved something devastating. No theory that preserves both locality and hidden determinism can reproduce the predictions of quantum mechanics. Experiments confirmed it. If reality has hidden instructions, they must violate locality. If reality is local, it cannot be secretly deterministic. You don't get both. This means probability is not a cover story for ignorance. It is baked into the structure of the universe. Feynman accepted this without drama, not because he liked randomness, but because the evidence demanded it. He once explained quantum probability using a simple but unsettling phrase. Nature uses probability amplitudes. Not probabilities, amplitudes, numbers that can interfere, cancel, reinforce. This is not how ignorance behaves. Ignorance doesn't interfere with itself. Quantum probability does. When two possible paths cancel each other out, the probability becomes zero, not because the particle avoids the path, but because reality forbids that outcome. The universe is not rolling dice blindly. It is following precise mathematical rules that produce probabilities, and nothing more. This forces a radical rethinking of causality. In classical thinking, causes guarantee effects. In quantum mechanics, causes constrain probabilities. The universe does not promise outcomes. It promises distribution. This is why Feynman rejected the idea that quantum mechanics is incomplete. Incomplete theories give vague predictions. Quantum mechanics gives the most precise predictions ever tested in science. It tells you exactly how often something will happen, and it is always right. What it refuses to tell you is which specific event will occur next. That refusal is not a failure. It is a feature. This leads to an uncomfortable realization. The future is not a single line waiting to unfold. It is a cloud of possibilities that collapses into facts only through interaction. Measurement does not uncover destiny. It selects from chance. And that chance is not a weakness of human knowledge. It is the engine of reality itself. Feynman understood how hard this is to accept. Humans crave stories. We crave reasons. We crave certainty. But physics does not exist to comfort us. It exists to describe nature accurately. And nature, at its deepest level, speaks the language of probability. Not because it is confused, but because it has nothing more definite to say. This is why attempts to restore classical certainty always fail. You can add many worlds. You can add hidden variables. You can add collapse mechanisms. But the core fact remains untouched. Quantum mechanics works without explaining which outcome really happens, because reality itself does not privilege one outcome until it happens. Probability is not a shadow of ignorance. It is the shape of reality before interaction. And measurement is the moment when that shape hardens into a fact. This is why reality feels stable only after we look. Before that, it is not undecided. It is probabilistic. Feynman's warning here is subtle, but devastating. If you demand certainty from the universe, you will misunderstand it. If you accept probability as fundamental, everything suddenly makes sense, mathematically, experimentally, and predictively. But your intuition will never fully recover.